Happy Thursday, Dr. Barth.
Hi, Eric. Welcome to Rubber Duck Engineering. Today,
Yes.
we are going to
ahead.
draw a line.
And a circle, if we're lucky.
If we're very, very lucky, a circle.
It's going to be, we're going to prove our real engineering cred that we could draw a line. We're going to do rasterization, which I've never done. I've known existed, but somebody had solved that for me in the library somewhere.
It's just something you just take for granted. You're like, oh, can't just draw a line. Boom, it's a line. But how does it work? Today, we're going to find out.
I was reading some about this on Wikipedia, and it's like the original algorithm for this was done in 1960. And that was like what we used until 2011 when someone came up with a better one. And then everything's on the GPU now.
Yeah, well, we're going to do software rasterization. So in reality, many people use GPU rasterization, but I figure we should start with software rasterization to see how that works.
Yeah. Anyways, this is going to be fun. This is our last episode of the year. This is the last week of the year. Next year, we'll be back with all sorts of fun stuff. I have not, it's been amazing. I haven't actually even been in this chair in a week. I've been eating too many cookies. Yeah.
Whoa.
My wife got a Switch, and so I've been sitting on the couch instead, which is terrible for my back. But anyways, been doing other things besides staring at a computer screen. It's been great. So
we've been doing a lot of fix-it projects around the house. Like there's like a switch that was like coming out of its socket, so we replaced it. And,
that's a less fun kind of switch than I'm playing with.
Electrical switch, not Nintendo Switch.
Shall we jump to the code machine and start making circles?
Yeah, you were in the middle of like hacking up a test harness for this, or like a.
Yeah. Well, there's a question of how do you show a grid of numbers. Anyway, so we made we made in the green room a little Flutter test harness. So we got to finish it.
We got to finish it. This is a professional show. We finish our tools en route.
Live on air. It doesn't compile. It's really close. I took if you saw our Lambda battle episode, I took the board out of that. Maybe that was it. I think I basically took the Lambda battle board and I hacked it together. But
so this blue area is being drawn like from a pixel grid, basically.
Mm-hmm. It's a 10 by 10 pixel grid filled with blue. I'll publish this code to GitHub very shortly, possibly even during the show. And then we were about to paint grid lines on it so you can see where the pixels are. And then we'll also need to center it because this should be a square and it's not.
Right. So for each height, so this should be something like J.
Mm-hmm. This should be like from 0 to
grid paint. Right. And this is like 0 to.
It's like size.left, right? Or is this a size?
How many do we have? We have pixels dot. This should be pixels dot width, which makes sense because it's going in the X position. Looks good. And then we'll just flip this around for here. We'll put the I in the X position. We'll put 0 in the Y position. Put the I here and the height here. And grid paint, or it should be like light gray or something.
Sure. Okay, it's sad at us. I haven't figured out why yet. 2 positional arguments expected for position.
Draw a line. Draw a line takes 2 offsets and a paint. Oh, we need to pass in the cell size.
Oh, yes. For offset for position, and then, yep. Mm-hmm. Anyways, this is not the episode. This is just the harness we tried to finish in 10 minutes before the episode.
Oh,
we have a comma in the wrong. Yeah, comma's in the wrong spot.
I think it's part of the episode. Like, how do you experiment with algorithms? You build a little test harness for them, right?
All right. There we go. Okay, can we make this center now? Where is it? I had to make my screen super big, so all I see is 5 pixels. Here, right here. This should not be a stack, but rather this is like an aspect ratio.
Yeah, stick in an aspect ratio.
aspect ratio, and then I think this is just child. What's that about?
Well, fewer brackets.
Aimed. Oh, aspect ratio. It's like 1:0. Aspect ratio. This is the body cheating, right?
What to put a center?
Yeah.
Here.
There we go.
That's square.
All right, great. I think we're ready.
Okay, let's draw a line.
We can change this from blue to white.
Okay. I'm gonna change. Okay, that's good. Black 26 turns out was dark. So I'm gonna try a different black.
The primary swatch, which we didn't need, or we don't need any of this.
Black 87.
Great. There we go. All right, we're ready.
Okay.
And just to confirm for people that this, like if we do var pixels, right? And do pixels dot set. I think we like set color, don't we? Oh yeah, store.
Store. I can say set color. You want it to be called set color?
That's really okay.
Set color.
This is colors dot black. It's color, fine. Should make a 5x5 black in there. Expected indent identifier. Oh. There we go.
Oh, I think we should do like, could we do like blue?
0, 1, 2, 3, 4, 5. Yeah, okay. Great. Great. So, great. So now the point was that we wanted to show you how to, given a line that is specified in floating point coordinates, how to rasterize it.
Right. Draw a line, and you're given in pixels.
Yep.
Antialiased, double, like a sub-pixel precision.
Yep.
Start X. Start Y.
Well, I got better for you.
You got better for me?
You just do what is it? Offset.
Oh yeah.
Flutter has this class, right?
Well, what a good idea.
What?
That's a great idea. And then a color?
Because then we're like literally implementing Canvas, basically, right? Except for it's a software canvas.
This is great. So, but now we need an algorithm.
Now we need an algorithm. Yes. Do you have one up on your screen, or I can dig out a? I can dig it out.
Yeah. Do you want me to paste it in the private chat? Or I can just copy. So what we do is we went to Wikipedia, and we look at. I'm really going to apologize for the name here. Xiaolin Wu's line algorithm, and they have it in. I don't know if this is Python or pseudocode or something. And we're going to try to translate it. It says end if, so maybe it's like Pascal or something.
Yeah,
I pasted it into our file now. If you want to go project it, I can look at it.
Where is it? Oh, I can start sharing again. All right. So I have a browser here. What did I do? Oh, I see. You pasted the algorithm. Great. So yeah. So this is the individual who in 2011
revolutionized the world of line drawing.
Line drawing while we were fading out into hardware drawing. Probably also at SIGGRAPH. I'm sure I'm getting this all wrong, but Wikipedia will set me straight. And there was a great image of this working. But yeah, so basically, I guess what we're just translating this to Dart.
I think we're translating this to Dart.
Maybe we should walk through what it's doing here. So this is the main algorithm, right?
Mm-hmm.
So from x0, y0 to x1, yeah? If we're steep, we do something different.
Okay.
We swap.
We swap X and Y. That's fine. We basically swap the start and the end. So they always want to be not steep.
Okay.
So they want to imagine the line going slowly.
Okay. And then we swap it around again so that we're always drawing with increasing X's or something?
Yeah.
Yeah. Okay. With increasing X's. Okay. And then we calculate the change in X and change in Y. We calculate the slope.
Mm-hmm.
If the slope was 0, we'll have to do this differently in Dart. Then we back up and we give ourselves 1 instead, because divide by 0 would have gone bonkers here. Would have done nothing. We round to an integer, because remember we're working in doubles to begin with. And then we figure out the yn, which is y0 plus the gradient times this rounded. What's this? Oh, this is the rounded times the distance. Is x0 not floating point? Is it pixel snapped?
Maybe it's pixel snapped.
We'll have to look at that.
No, we wouldn't need to round it if it was pixel snapped. I don't know what the types are here.
Oh, we do. We round it.
Yeah.
So why is this?
I think it's basically projecting forward. I see. It used the yn to compute the gradient, and then wants to recompute yn using the gradient. So you don't have any. So everything is going to add up in the end.
I see. So you don't get floating point math errors.
Correct. So they're recomputing where the yn is going to be, basically starting from the intermediate values that they computed.
Okay. Yeah, if I was analyzing this by myself, if you weren't here, I would just like write a comment in the code being like, I don't understand what this does. And I would come back to it, 10 minutes later when I did.
Mm-hmm. What is RF part? That's a function they defined earlier. RF part is 1 minus the F part.
So this is the rational part as opposed to the fractional part. Am I saying that right? When you like split the before the mantissa and after or whatever.
Possibly. So let's see. X minus floor. This is like the amount greater than the integer, and this is the negative of that.
Okay. X minus floor.
So like if X was like 1.2, this would be 0.2.
This is 0.2. So this is the fractional part.
And then RF would be 0.8.
Oh. I had expected this to be the 1.
I mean,
yeah. Okay.
Okay.
I don't know what that's used for, but sure.
Okay.
Where are we? Right here.
That's the gap.
Handle the first endpoint.
Okay.
Okay. So we're just going to hold on to that. This is where what the hell is that doing?
I part, I think, is for 1.2 would be 1, the integer part.
Okay. This will be used in the main loop. Okay.
Okay.
If we're steep, this is back again. We need to, you almost feel like this should be written.
Yeah, like pull apart. They're trying to like share code between things that really should just be two.
Yeah, you just flip things around and then call the non-steep, subfunction or whatever.
Yeah.
But okay, so we do something different, and then we're plotting yp. Oh, so plot is the draw pixel.
That's the draw function. Yeah.
Yeah. So this is the y pixel 1, an x pixel.
X pixel 1.
And then this weird RF part times the X gap. This is their color intensity, right?
That's the intensity, right? So they split the intensity. That's why they want the RF part. There's so they want 0.2 and 1.2 because they always want the intensity to add up to 1, right?
Yeah.
So there's the Y pixel. There's they're drawing the 2 pixels stacked top and bottom.
Yep.
Mm-hmm.
Makes sense. And this is why they always want it to be not steep.
Right, because they want to sort of conceptually scan across.
Mm-hmm. Okay.
Yep. Okay, that makes sense.
This would make more sense if we had a visual, but yeah, we'll get to the visuals. Well, I don't know what intery. I don't know what that means.
Inter Y.
Inter Y. Okay, Y end plus gradient. First Y intersection for the main loop.
Okay.
I don't know what that means, but sure. Handle second endpoint.
Okay. Pixel 2, blah, blah, blah. And
Okay,
then do
sure.
the main loop.
And here again, we have the steep versus not steep.
Uh-huh.
And then for X from pixel 1 plus 1 to pixel 2.
So basically, they did the two end caps, and now they want to fill in everything in between
with some generic algorithm.
Right.
Where we do the I part, and this is the splitting of the intensity. This is the anti-aliasing part going on.
Yeah, and they're computing the Y incrementally instead of recomputing it each time, which is why I think they do the reprojection of the endpoint.
Okay.
This looks numerically unstable to me. Like I would be concerned that you keep adding floating point numbers together. If you're in sort of a, depending on where you are in the floating point number line, you get varying amounts of precision when you do this.
And maybe they do that by asserting that we're within a certain range of the floating point.
Well, I mean, when I used to work on GPU drivers, and what we would do is basically, the developer thought that they were working around 0 because they always want to program around 0, but you would actually do all of their rasterization like way, way far from the origin where the floating point numbers were much more stable.
Oh.
And so you just do this numeric transform way over there, do all your drawing, and then like put it back.
Okay.
Otherwise, the rasterization, you get into these like numeric precision issues where the closer you get to 0, the more precision the floating point numbers give you.
Yep. Okay, I think we have enough to like start sketching.
Yeah, I don't think we should tweak this algorithm. I think we should just try to implement it as is.
Well, I would argue actually we should only implement the steep or non-steep case or whatever. Right.
Okay, let's implement the
non-steep case, and we just assert bail in the.
Okay, that's fine. That sounds good. So should we just start by translating some of the simple functions, like the plot function? We could probably do, right? Well, the plot function we have, right? Oh, we don't quite have the plot function because we need to set the color and an intensity. So I'm going to add a plot to our pixels class. Plot. Double. Okay, it's going to be really easy. With
I'm not watching you do it, but I can also imagine it in my head. Yeah, you're just taking a color and your intensity, and with opacity.
Oh, opacity is not quite right actually, because that's good. Then it's going to blend with what's underneath it.
Isn't there like a pre-multiplied alpha kind of thing?
Yeah, I think we just want to multiply it in. So we're really going to.
It's also okay if we get it wrong here.
Color from RGBA.
Sure.
Red times intensity. Red, green.
Yeah, like I have no idea how this works with alpha.
You just pass the alpha through. Blue times intensity. And then this seems to be made back into an integer.
It doesn't seem to like you're from RGBA. Is it ARGB?
Probably. I don't have autocomplete on my screen, so.
Yeah.
It's like that?
Like ARGB, yeah, it does.
And it's not going to like the fact that it's going to want these to be integers. So we're going to need to say like,
we also need to assert intensity is less than 1.0. you want a separate type in Rust.
Okay.
Okay.
So that's the plot function.
Great.
The integer part is floor. Round. I think it's just round. This looks like Dart round. Fractional part, I don't know if Dart has this. We can write this.
I would expect it to. Rust has it.
Let's find it. It's not.
I think if you just do like 1.0 dot. Maybe it doesn't. Dart is really conservative in what it adds to the standard library. So.
Okay.
Fine.
Then RF part is.
So I'm going to delete all these.
Okay. Okay. So we got RF part.
Okay.
All line. Where's our draw line prototype?
We can move it up here. There we go.
Okay. I got it. I moved it.
Great. Perfect.
I'm gonna put all this stuff inside of it. Okay.
Okay. And
so you just want to assert that it's steep.
Yeah.
Or not steep.
Bar steep. It's like this is really want your like delta.
I think offset has a delta. Delta y, delta x.
N minus.
This is just final delta equals n minus start.
Mm-hmm.
And then you should be able to say delta dot dy.
What is it? dy, yeah.
Greater than delta dot dx.
So this is abs. Which I think it's on, yeah.
Okay.
I'm just going to do if we're going to assert using assert's a little lame because it won't run in production. But
we'll use the magic to do function.
Okay.
Okay. Nailed it. I delete this as we go.
I think so.
Okay.
I mean, I only have 5 pixels. I only show 30 lines on screen, so we got to be conservative.
Then I'll compress this to one line. It'll be amazing.
Swap x, y, x and y0 and y. Is that just making start equals to end and end equals to start?
Yeah, but we can do that, right? So we can say if start dot dx is greater than n dot dx, then is I don't know. Is there a nice way to do swapping in Dart?
I don't know of one.
Yeah, I know that so rarely. I don't know. Okay. Oh, this works. Right.
Okay, we already have dx, dy. Oh, they're the wrong ones, though. We have to update it now.
Okay, so let's write this. So final delta equals, and let's start again.
We could also just. Okay.
Let's assign it. The final anymore. Okay. Nailed it.
Well, this needs to be var.
Okay.
We should also just move this into there then. It's lame, but
Yep, that's a good point.
a little error prone, but yeah.
Okay. Gradient equals delta.dy divided by delta.dx, right?
Mm-hmm.
What's going to happen if we get divided by 0 here?
Uh,
Oh, we can just test it above, right? We can just say, before we do the division.
correct.
Right? We can say, if this thing was 0,
Mm-hmm.
then 1.0. Otherwise,
Yep.
this. Okay?
I actually think that it might be a silent. I don't remember what Dart's behavior is. Rust would definitely blow up.
Well, so this would have to be, if delta x is 0, this is a vertical line,
Mm-hmm.
which is going to have to be steep, which we've asserted that it's not steep. So I don't think this can actually happen for us.
I see. Because you get thrown down the steep, you try and recover, but then you still hit this and
yeah, or maybe it can only happen if the line is 0 width or something, 0 length. Anyway, it's fine.
We could talk about, like, we could start keeping, if we were actually going to ship this, right, we'd test cases, right?
Yeah. Oh yeah, definitely. Vertical lines, horizontal lines, zero length lines. Okay, final x end equals start dx
It would be x end.
Okay. Double. We want to keep with doubles.
Does round not round double?
Well, round will give you an integer.
Uh-huh.
Y. Now here's the thing we talked about before. We like reprojected the y. Start.dy plus gradient times x end minus
Start dot
dx. Okay.
Okay. Yeah, it's a little weird. Okay. Mm-hmm.
A little weird, what?
Well, just it's like separate handling. Do these need to be? Well, we'll see when we write them out. Are they really that special, or should they be like a shared function? It's like the draw endpoint.
Yeah, I think once we have it working, we can try refactoring a bunch of different ways. I expect they wrote it this way just because this is like a Pascal-y way of writing it.
Sure.
And in a modern language, you'd probably like factor it quite a bit differently.
Mm-hmm. X pixel 1. So this is.
X. We can also just like we have letters, we can use them.
Yeah.
XN. All right, very good. Yeah, I don't know. There must have been like a shortage of letters in the early computing times when it was.
We only had 80 columns, man. They didn't have a 4K monitor.
but even with 80 columns, like how like I don't know.
I don't know. Punch cards.
Y end. The integer part is floor, right? Okay. This will be used in the main loop. Yeah, good to know.
Thanks for the hint.
Well, I might as well preserve the comments all right. Okay.
Yeah, I know.
So if steep, so
we don't do steep.
to do it.
I see. To do steep.
If to do steep something.
In Google style, that would mean go ask Steep.
Go ask email.
Whoever has the LDAP Steep.
Okay.
Yep.
Okay, now we have our plot function. Nailed it. Okay, so plot function we can say
Pixels dot.
Yeah, we're gonna inflate these and hydrate their vowels.
Pour a little vowel fertilizer on them.
Yeah. Also, they're capital letters. Maybe capital letters didn't exist in early computers.
I think not. I think
shift key was.
You had to have an extra special keyboard for that.
Okay, and now you can start to see. Also, they had their like bespoke white
space. This wasn't early computing. This was 2011.
There's no excuse for the vowel. There was no vowel shortage in 2011. Okay.
The great vowel shortage.
The great vowel shortage.
Okay, why is this all pixel 1? Did we?
Oh, there's no intensity.
Did we pixel 1 too many times here in your plot here?
No, this is supposed to be y pixel 1. Oh, maybe. Uh-oh.
Uh-oh.
Poorly inflated. Yeah, y pixel. In the Y position goes Y pixel, as one might imagine.
Oh, I see. Because in the steep, they swap the X and the Y.
We didn't give the color that we wanted here.
What? Windows, you are useless.
What does Windows say to you?
Windows is telling me that they didn't find anything in their scan of my hard drive that they helpfully ran at perfect timing.
Okay, so before we go farther,
why is this sad panda here? Oh, because it's like an int
integer.
I see. We gotta turn these into.
Oh, they wanted round without rounded double, is what they're saying.
Oh, I see.
Okay, I think we can try just run this part of the algorithm and see what it draws.
Okay, well, so we should draw something from like 1 point, Yeah. All right. Great. All right, so we can do this. If we get really fancy, we can have it draw out on like an animation loop.
That is super fancy, but let's just start with something basic.
Yeah, no. But just in our
draw a line.
Yeah, exactly, right here.
Offset, and you like blue?
Yeah, so I think if we did like 3.0, let's see, X should be like 1.2,
okay.
And the Y can be 2.4, 2.3, something like that. We're going to 7.4 and
9.8.
Y is 3.6.
That's going to be steep.
Steep because it's too flat.
Oh no, that's right. You're right because you're changing X a lot, which is good.
Is that better?
That's better. It's going to want
45 degrees. Wants more constant.
Insert more Vespine const. You don't know StarCraft yet. You will after watching many of these episodes.
By the 79th episode.
Our intensity calculation was not legit.
What? Our code is always perfect. First time.
Why don't we just, for the sake of our sanity's sake...
Whoa. Hey, it drew something.
It drew something, but we're just going to always draw in black and white for right now. 255 times intensity. And round that. So we'll figure out how to apply the color later. I think we have to apply the color in HSV space. Is part of the problem.
Okay.
Let's just try that.
I see. So you're just ignoring the color?
I'm ignoring the color and just making a gray of the appropriate intensity.
Okay. Is that correct?
Well, what did you ask it to do? You asked it to draw...
Can't find my way around this darn file.
Somewhere we asked it to draw a line.
Somewhere in the 5 pixels. Here we go. Yeah, draw a line. Pixels from 1.2. I really want to save this, so I want to draw these.
This looks plausible. It's about there, right? It's about at 1 point. It's about 1 over and about 2 and a little down, right? Because it's 0. The first column would be 0.
I hear you, but like my life.
The code is too ugly. You're just like your brain cannot process more input while the code is ugly. Please hold while the code becomes beautiful.
There's that, but also like I really want to pass these in, or I want to draw them on top of the pixel view. Right? I want to draw a little circle at the start and at the end.
Okay, but let's keep going. But I think we'll get there.
Okay.
But I think if we go down that route, we may not finish drawing our line.
Focus on the prize, Eric. Okay.
Okay. So good. We plotted our first point. Okay. Now we got to translate. We got to add all the missing vowels. Inter. What do you think inter means? Intersection?
First Y intersection. First Y intersection. Okay. Intersection Y, but that doesn't make any sense either. But go ahead.
This is a mutable variable. Intersection Y equals Y. I guess this is Y intersection, right? Just for consistency. Okay. Also, in the early years, the Y's came before and after. Okay, plus the gradient. Okay. We shouldn't make too much fun. It's just funny.
Yeah, we should like be bowing in front of these people who made these amazing algorithms that we use.
I could never come up with this algorithm. I don't know about you, but okay, we got that. Okay, handle.
I have never presented at SIGGRAPH, so
I wrote a paper for SIGGRAPH, by which I meant there's one page in a SIGGRAPH paper that I wrote.
That's fantastic.
It was fun. I had very little knowledge of what I was doing, and I luckily worked in a lab with a bunch of people who knew what they were doing, and it was good times. Okay, y end. Okay, so y end is changing, so these things are going to become vars now. Okay. And so this is the end.dx round. Okay. Y end. This looks similar to what we wrote before. I'm going to write this out just to see what it is. N.dy plus the gradient xn minus n.dx. What's that different from what we wrote before? Oh, we did the same thing, but with start.
Basically, yeah.
Okay.
So this
is like, yeah, this is like compute the y value that corresponds to this x value. Although here's why it starts at the end. Interesting. Okay. Okay, x cap is becoming a variable again.
We should also say that this algorithm was written to be fast. This doesn't say you need to write obscure code in order for it to be fast. I'm just saying that there may be trade-offs that exist in whatever this was whatever was written down in Wikipedia was translated from something else.
This still will be used in the main loop. Okay. I think it's basically these intermediates that we're calculating are used in the main loop, but the y's are not, like the x's are.
Okay.
What they're trying to tell us. Integer part of y end.
Okay.
Okay. So far, so good. So these functions are actually quite similar.
Yeah.
Which makes sense. They should basically be the same, except they're at a different position. Okay, so steep. If steep, do this. Good times. Mm-hmm. Okay, if not steep, which is us, then we're going to do this.
Yep.
Okay. Correctly hydrate the vowels. X pixel 2. Pixel 2. And the gap. And the gap. Okay.
Okay. What do we do?
Pass the color. Okay, so now we should see the endpoint appear. Boom.
Yep.
I'm worried that they're both dark.
Yeah.
They both seem dark to me.
Why is this always from YN that we're computing there? I wouldn't expect that.
Because the X is like fixed, and we're interpolating like where are we in the Y, right? Because it's a shallow line.
Okay.
This doesn't seem right. The fact that both these pixels are very dark.
Mm-hmm. I agree with that.
But what number did you
maybe
pick?
It could. You can get that behavior.
If it's like 50-50? It's like what was
that if the line continued at all to the right, I think we should fill in the rest.
Okay. I'm just going to change this. Just for curiosity's sake, I'm going to change the end to be 6.0 in Y. We can change it back to 6.6.
You see it move up.
Yeah.
That seems wrong.
6.1. Yeah. So something's not quite right. That's okay. I think we should keep going and we can debug it. But I'm gonna make a note here. Okay. This seems to be drawing too many arc pixels. Okay.
What is the X gap?
The X gap is the RF part.
When the intensity goes up, does it get lighter or darker? Like if I make this one like 0.1.
That should be light.
Oops.
Oh, we have it backwards.
It's not very light.
Yeah, we have the intensity backwards. You're totally right.
All right, so yeah, so I undid. Okay. Anyways, where that could end up, yeah.
Minus intensity. Okay.
Okay. And we're both very light, like too light.
It's possible. Let's keep going. Too many light pixels.
Sophisticated programming at work here.
Oh, you know what? I bet the reason why. Oh, I get it now. Here's my theory.
Good.
So for the intermediate parts of the line, the full range of X values is covered, right? But for the end caps, you're only covering some fraction of the X. And so the X gap is telling you how much of the X you're covering. And so the end caps could be arbitrarily light.
Yep.
If you just barely enter that X.
Yep. I get it. Yep.
Okay.
I agree.
Because actually, it's plausible so far.
Yeah. But again, that still points to that this could be, these can get, these will get refactored out.
Yeah.
This is going to end up being like 8 lines long.
Okay, so now let's complete the middle part of the line. Main loop. Okay. I think
So here again, we don't steep.
All right, I just leave that whole block there for if steep. End function. End function.
That's good. We needed an end function in our lives.
Okay. That belongs to you. Okay. For loop. Int x equals.
We saved this off, right? X picks 1 and X picks 2.
While x is less than x picks 2 plus plus.
And X picks 1 and X picks 2, those are like X. End? Yeah. Yeah.
Are they integers? No, they're doubles, right?
They should be integers.
No,
right?
they're integers.
Wow.
They're integers.
Yeah.
Okay, that's legit.
But these are like, yeah. It's like the X picks 2 is the penultimate X.
Correct. That's why we say less than.
Yeah.
Yeah. Okay, so we need to plot function x.
I part of your y intersection.
Your y intersection.
Howdy, TechX.
Hi. Thank you for joining us on our line drawing adventure.
Yeah.
I think this is like interpolated y. I'm just going to rename this to y. Okay.
Okay.
Is this the only first place it's used?
I see. It's like calculated y.
It's like a peer to the x, right? Right? And then the same thing. So we're gonna say final floor y equals y dot floor. Okay. This is y floor. Floor here. We're like marching along the y's, and we have to paint 2 pixels. One for the RF part and one for the And then we march in this, what looks to be numerically unstable, but it's fine, I'm sure.
You can see us painting them. Because Flutter. There you go. That's reasonable.
Well, hold on a second. I have a question. The X pixel 1 plus 1.
I don't understand why it's so not regular.
I don't think we have it right yet.
Like, I would expect it to be symmetrical, if nothing else.
We didn't give it symmetrical inputs, though.
That's true.
I mean, it kind of looks like a line.
I also really want to draw the circles and the line on top of it.
Well, can we just try to draw like a horizontal line for like a control?
Sure.
Like, I don't have a ton of confidence in this implementation. The algorithm I have a ton of confidence in. The implementation.
Will our horizontal line be steep?
No, vertical line would be steep.
Where are we? All right, let's.
Yeah, I think we do a bunch of simple cases. Like, can we draw from like 1, 1, 1 to
1.0.
Well, you have to do that's going to assert. You need to do that was steep. You need to make the x's change a lot.
Oh no, that was a mistake.
Assert was really a big hammer to pull up here.
I have to hit the button. There we go.
We also don't have a lot of bounds checking on our. If you try to set our integer array out of bounds, it'll also assert.
I mean, I can also just make those asserts like log and return, but
that's fine. We'll just be careful to do the math right. I think we should log and return. That's a good idea.
Okay. Did you launch? You compiling Windows? Like all of it? You're compiling Windows.
My favorite thing about developing Windows is you include Windows.h, but Windows.h is too much. And so you define this thing called Windows lean and mean. It's like, I want a small Windows header, and then that's too much. And there's another one that you define that's like, no, like super lean and mean. I really mean it, Windows. I don't know who thought they should put the entire operating system into one header called Windows.h, but it was.
Okay, that looks reasonable.
That looks reasonable.
Well, but why is it bleeding in?
Right. I think our end cap is not correct. There's something wrong with our end cap calculation.
Those should be. Oh, so if I recall correctly, this algorithm assumes the floating point that the pixel values are in the middle of the pixels.
Oh, I see. Okay, so we should really go from like 1.5.
I think so.
Okay, that seems fine. Let's try to do that.
I feel like I recall reading that in Wikipedia.
So just like throw 0.5 on all these things.
Yeah.
Okay.
Okay. So there it feels like it's assuming it on the x direction, but not the y direction.
Okay.
All right.
We drew the simplest line possible, but we nailed it. So that was good.
Okay.
So what happens if we just go down like 1?
That's still wrong, though.
What's wrong about it?
Well, why wouldn't it be symmetrical? I see. Well, how many? This is 5, right? So if we did this with 7, now that would be 6, and that should be symmetrical?
It looks pretty symmetrical. What's not symmetrical about it?
Why is the end one?
I see there's 2 dark ones.
But maybe it's because it's not even, right? So if we went to 0.5 and 8.5, right, that's going to be, no, still, you get this tail. That seems wrong.
Okay.
Oh, do you have the tail on state? No. Yeah.
Okay, so let me try less than or equal here.
This, I imagine, is not how the algorithm was developed, by the way.
You don't think it was developed in hot reload in a
Well, yeah, high reload didn't exist, but
in a test harness that already had a complete vector graphics
running on the GPU.
Okay.
So something's wrong with our like main loop.
Something's wrong with, yeah, I think there's something wrong with the, well, let's just take out this plot here. This was the final pixel, right? So let's take out the start pixel and the final pixel just to see, like, so this is the stuff drawn by the main loop.
Yeah, so why is one end darker than the other? Right. Okay, so this should be.
These are good questions.
0, 1.
Well, what happens if I if I get rid of this +1 here?
Also, why is it starting? If it's starting from 0.5, this is the 0 pixel right here. Why isn't it drawing starting in that pixel?
Okay. Okay, I'm gonna put all the draws back.
I wonder if we have an off by.
Yeah, if it's 0.1, I think we should be coloring it. I think the end thing is correct, and I think the beginning is missing a dark pixel at the beginning.
Oh, right? Okay, that could be.
Because we told to start at.
Well, I wonder if we're drawing if we're double drawing that.
Yeah, like if I go delete the first pixel draw,
no,
it does disappear. Okay. I agree. That seems off because let's think about what we told us to do. We said go from an x of 0.5, right? And a y of 1. So I would expect that left pixel to be filled in. You're going to draw it? I agree.
I'm hacking it in, man.
Do it.
I just couldn't take it anymore.
No, I think this is exactly the right time to do it when we're trying to debug this issue about starting and ending.
I mean, it's a little lame that I'm like, the way that I'm hacking it is relatively terrible, but
you're just gonna draw like a dot, right where you want it to be.
I could do the draw dots as well as draw line. Right, so canvas, draw. What do I do? Canvas, draw line, start, end. This needs to be times the cube, right? Or times the.
There's offset for position is what you want.
Oh, sure. But position is integers, isn't it?
Oh, I see. Yeah, times the cell size.
I don't know if that'll do that, but should.
I don't know if it will.
This needs to be like line paint.
We should pick like a debug color, like red.
Pink or whatever, yeah.
Okay, pink is good.
So we don't know how to multiply too many positional arguments. What did I do?
Yep. Yeah, I don't think this multiplication is legit, but
You can fix that while I fix the plumbing.
okay.
What did I do? Too many. How do you might complete normally? Oh, I see you're doing it. Offset for offset.
I mean, what do you want me to call it?
translate to local? I don't know. Like
local to canvas.
Sure. I guess it's what it's doing.
Yeah.
That's what all of these are doing.
Yeah, you look at this like what coordinate system are you in problems.
Yeah.
You need to like have nice names for all your coordinate systems so you don't get confused.
So this is dx and this is dy. Because we're dealing in offsets for whatever reason. Okay. Okay. So why is it not pink? Why is it just... Oh, also it needs a line width.
Yeah.
Looks like you're doing it. Oh. Yeah, it also needs to be set to stroke, right? Mm-hmm.
Was it mode?
Well, we promised a circle, but we're going to get a line.
We're getting a line. I think line is pretty neat. I don't have autocomplete, so you have to tell me what the paint mode is.
This is probably stroke width.
Why don't you do this? Let's see what the autocomplete.
Stroke width. And this is going to be...
So what are we doing with 0.5,
like
right? There's the 0.5 also, right?
Well, yeah, but the 0.5 is only in the X for some reason. Okay.
Yes.
So that makes it look like just the last one has an extra pixel for some reason.
Well, I can't see. Why is the
why
isn't it pink?
How do we get this? We get stroke width. I see. Maybe this style is... What's going on here? Oh, because it's not using line paint is its problem in life.
Oh, that'll do it.
There we go.
There we go.
Okay. So we seem to be bleeding too far past the line.
Do I do this? Okay. So did our y? What was our y values that we were drawing?
What was our y values? This is in main. No, this is in...
Okay, yeah, our y values are integers. So what else we put in 5 in our y values?
At least making
Yeah,
fast.
I think we're not. Our holding is shifted one too far. Right? Let's even try without any change in this. Yeah, so this makes it really quite clear, right? 0.0. See, our pink line is where I would expect it. Okay, can you see the pink line?
Mm-hmm.
I guess I can move the Y 2 down. See things better. See, the pink line is shifted 1 over to the left.
Yep.
From where, so should we read our algorithm and try to figure out why that is?
So is 0.5 rounded up or down?
Right. Maybe that's the whole thing. So like if we should say...
If we just did 0.4, what happens?
Try it.
Where'd it go? I get so lost on this tiny, tiny monitor.
But see, 0.4 is over the edge, but it's only a tiny, tiny amount. Like it drew that pixel, which was good, but it was really light, whereas I would expect it to be like 50% shaded. So 0.5 was rounding up. Okay, and then what color did it? Like, is this really supposed to be x plus 0.5?
Is it? Are we supposed to be drawing x pixel 1?
I mean, this is what this does, right? The start x is like 0.4. You add 0.5 to it, you get 0.9. You take the RF part, is 1 minus the F part. So it's going to be 1 minus 0.9 is 0.1. Like I would have expected this to be just the F part. You see what I'm
And on
saying?
the other side, also the F part?
I'm going to put it back. On the other side, let's think about this. So let's say this is like 0.6. So it goes to 1. 0.6 plus 0.5 would be 1.1. Yeah, so what if this was the F part as well? Yeah, I think these are supposed to be F parts.
Transcription error?
Yeah.
I mean, now the line is overdrawn slightly, but maybe correctly because these are antialiased, right? These are not drawn full pixels.
Correct.
But why is this? Why are we bleeding down here?
Oh, because I moved it down a little bit, just so we could see things better. I can change this back to 0.
Oh, I see. But still, why was it? Oh, I see, because it's thinking the line is 1 pixel wide. It doesn't quite fit in that.
Yeah.
Okay.
And this looks better. I wonder if it's just a typo about the RF part.
I suspect so.
And now what happens if I make this 2? That looks more symmetrical, doesn't it?
Still not entirely. Like this second, I don't know how well this is coming through on the video, but the second, it looks like lighter to darker to lighter, whereas this ends with darker, lighter. Like,
yeah,
this second pixel is darker for some reason, suggesting the main loop is somehow starting at full darkness in a way that it shouldn't be. Right, like somehow it's bleeding more on this pixel here than it is on this pixel.
Yeah. I'm sort of losing confidence in the Wikipedia translation. I kind of want to go back.
Yeah,
to
we have to go look at the original paper or whatever.
Or maybe just some other implementation to sort of see. But anyway, we've also reached an hour. I thought this was super interesting. If I were doing this, I would continue to debug this and look at another reference and try to understand whether this was actually correct. Because it doesn't seem quite correct yet.
I also think that...
I need to put it back to RF, just so what we have matches what Wikipedia has.
This was intended to be a one-off episode, and it's very hard to judge how long these things will take. But I think what's interesting here is that we now have a harness we can play with.
Well, the harness is super useful. Like the ability to like draw on top of it and like look at all these things is I don't know. It's just so hard to just do this numerically, like in a console or something. But yeah, I think this is a good.
But I think there may be more episodes. Like I think there could be more interesting, drawing sort of episodes to do. But
Yeah, I mean, maybe we'll do a circle someday. That'd be cool too.
Well, any last words for our viewers for 20? What the hell year is it? 2021?
No, I just want to wish everyone, a happy new year and best of luck, everyone, in 2022. I think everyone is hoping 2022 will be a better year than 2021. I'm certainly hoping that for myself.
Yeah, I would say the same. Just everybody stay safe in the holidays. It's certainly it's a little nutty here in California. Certainly, people are all excited about all these things going around.
So, yeah, thanks, Kilo.
Happy New Year. Happy New Year, Kilo. Happy New Year, Tex.
Yeah, and we'll be back in January on schedule.
Yep. We'll see you next week.
See you next week.
Take care.